In this video, we're going to have a little bit of an introduction to redox, so oxidation and reduction reactions. So in general, oxidation, reduction, or redox reactions are the things that power all of our ecosystems, whether we're talking about a city or a natural system. So as a reminder, oxidation is loss of electrons and reduction is gain of electrons. And what do we personally oxidize to gain energy? So you can pause and think about that. And the answer is organic carbon, things like glucose, anything we eat, really. So we get the energy out of this carbon by breaking these high energy carbon-carbon or carbon-hydrogen bonds. And the oxidation of these bonds or breaking of these bonds releases this energy. And here this is showing you for aerobic respiration, we just call this respiration, this oxidation of carbon. Releases this much energy. So the change in energy is 29.9 kilocal per mole of electrons. So here we're oxidizing carbon. It loses an electron and becomes CO2. And the oxygen is reduced. It gains electrons and forms water. Okay, there's another way of thinking about it. So we have glucose, high energy, carbon-hydrogen, carbon-carbon bonds. You can think of that as sort of having a lot of energy, maybe like a rock sitting on top of a hill. And oxidation or respiration rolls this rock down the hill and reduces energy. Again, looking like this. So respiration changes these carbon-carbon bonds into lower energy carbon dioxide, carbon-oxygen bonds. Okay, so heterotrophs, which is what we are, consume and oxidize or respire organic carbon for energy. So we have to eat our carbon to get it. So here is a thought question for you. Do plants oxidize carbon or do they respire? You can pause and think about that. And the answer is that everything needs energy, so everything respires, even plants. The difference is that plants don't eat their carbon to get it. They make it themselves. So they're autotrophs. They use energy and sunlight to make organic carbon, which they then respire for energy. They can also use it to make biomass, but they also respire some of it to get energy. Okay, so the main points so far, oxidizing carbon and organic matter releases energy. So this is respiration, and both autotrophs and heterotrophs respire. They break these carbon-carbon bonds to get energy. Okay, so another main point is that energy flows through ecosystems. It doesn't cycle, it's not conserved. So energy in organic matter can't be transferred or oxidized with 100% efficiency. So some is always lost as heat, and you've probably seen something like this before. That primary producers have a lot of energy, and for every level up that you go, more and more of that energy is lost as heat. Okay, so without a constant source of energy, in our case that's usually the sun, to reduce carbon, which is what plants do, ecosystems won't work. There won't be any energy to make them work. Okay, so main point so far, oxidizing carbon and organic matter releases energy. This is respiration, and energy flows. Some is lost as heat with every transfer up the food chain. So we need energy sources like the sun to keep ecosystems going, to keep them functioning. Okay, so if we're oxidizing carbon, where do the electrons go? So here are your choices, the oxygen in water, the hydrogen in water, or it depends. So you can think about that for a moment. And as you may guess, the answer is a little more complex, so it does depend. And part of this has to do with the idea that oxidation and reduction happen at the same time. So this is aerobic respiration, so respiration in the presence of oxygen. And when this happens, we oxidize carbon to carbon dioxide, and we reduce oxygen to water, and that releases energy, as it shows you right here. And here's a little mnemonic that I actually still use to this day. Oxidation is lost, reduction is gain, or oil rig. So you can use that to try to remember if you have issues with that sort of thing, like apparently I do. Okay, so the amount of energy gained from oxidizing carbon depends on what is available for reduction. So if there's oxygen available, it's used as the terminal electron acceptor. So it is what accepts the electrons and is reduced. And in this case, you get a lot of energy for using when you use oxygen as the terminal electron acceptor. But oxygen isn't always available. So in some cases, you may have a reducing or a more reducing environment where you don't have any oxygen available. And in this case, maybe you don't have any oxygen, so you use nitrate as a terminal electron acceptor. And you can see that there's less energy. You get less energy from doing that. And the same is true when you start using these other terminal electron acceptors as you go on down and get into a more and more reducing environment. So we're going to talk more about EH and PE in class, but in general you can think about this axis as being a decreasing tendency of these terminal electron acceptors to gain electrons. So they don't want electrons quite as badly as something like oxygen does up here. And as you go down this sort of ladder, you get decreasing energy gain from carbon oxidation, and oxidation gets slower. It doesn't happen as quickly. So that's the next sort of point, is that aerobic respiration, that just means that there is oxygen available, and that oxygen will be the terminal electron acceptor. So anaerobic respiration, that just means there's no oxygen available, uses other terminal electron acceptors that provide less energy. And then these redox conditions matter for biodegradation. How fast is carbon going to be degraded, and how much energy is our organisms going to get from that carbon? And then it also matters for aquatic life, which may need oxygen. And that's all we're going to talk about for redox chemistry in this video. So thanks for watching.